Hello students, today we will be seeing Relations and Functions exercise 1.1. A small disclaimer, the images, text and other materials used in our presentation are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the same. Thank you. Here's our question. Show that the given relation R in set A of points in a plane given by, so our relation is collection of all pairs P comma Q such that distance of the point P from the origin is same as the distance of the point Q from the origin. And we have to show what? That this R is equivalence relation. Further, we have to show that the points set of all points related to P, which is we are taking 0, 0, we just taking any point but not 0, 0 related to P is the circle passing through P with origin as center. I hope question is clear to you. You will have some seconds to try this problem, then afterwards we will move on to the solution slide. So your time starts now. The time is up. So in question we have to show the given R is equivalence relation, and further we have to show points related to point P is set circle passing through P with origin as center. Set of, so what we have to show is second point, show that the set of all points related to P forms a circle passing through P with origin as center. So solution. So in order to show equivalence relation, we have to show 3 points, reflexive, symmetric, transitive. So starting with the given relation, clearly P comma P related to P comma P, this pair belongs to the relation R. Why? Because the distance of point P from the origin is always the same as the distance of the same point P from the origin. So reflexive. Now assume P comma Q belongs to the relation R, meaning if this belongs to the relation R, meaning P and Q satisfying the condition, which is the distance of point P from the origin is the same as the distance of the point Q from origin, which implies the same thing can be said by different words, which are the distance of P from origin is same as the distance of P from the origin. So distance of Q from origin is same as distance of P from origin. So this gives me Q comma P pair belongs to R. So R is symmetric. Now for transitive. So in order to show transitivity, we start with two pairs PQ and QS, and both belongs to the relation R. So according to the first, the distance of point P and Q from origin is same. Also the distance of Q and S from origin is same. So which we can easily conclude that distance of points P and S from origin is also same. So P comma S pair also belongs to the relation R. Therefore, your R is transitive. So we have shown R is reflexive, symmetric and transitive, which implies R is an equivalence relation. Now the set of all points related to P and P is non-zero point will be those points whose distance from the origin is same. Yes, whose distance from the origin is same as the distance of the point P from the origin. So, and if you paid attention to the words, this is same as saying if O is your origin at 0, 0 and OP length is R, then the set of all points related to P is at the distance of R from the origin. This gives me a circle with center origin, radius r passing through the point P. Clear? Moving on to next. This question. Show that the given R defined in the set A of all triangles, set A is of all triangles, and R is defined as collection of all pairs T1, T2 such that T1 is similar to T2 and this R is equivalence. We have to show. You'll have some seconds to try this problem. Then afterwards we will move on to the solution slide. So your time starts now. The time is up. So we need to show that the given R is equivalence relation. Solution. So in order to show equivalence relation, we need to fulfill three conditions or three relations type: reflexive, symmetric, transitive. So now for first, any triangle is similar to itself. So fulfilling the condition of reflexivity. Therefore, if you pick any triangle T, it must be similar to itself. So T, T belongs to R. For every T belongs to the set A. So R is reflexive. For second, we need to show R is symmetric. In order to show R is symmetric, we start with T1, T2 pair belongs to R, which gives me T1 is similar to T2. And this is same as saying T2 is similar to T1. So from first, we started with T1, T2 belongs to R, and this gives me T2, T1 also belongs to R. So symmetric. So R is symmetric also. Now for third, transitivity, we always start with two pairs. So first one is T1, T2 belongs to R, meaning T1 is similar to T2, and second one is T2, T3 belongs to R, meaning T2 is similar to T3. Now you can easily see that T1 is similar to T2 and T2 is similar to T3. So congruency, or not in this case, the similarity in triangles also transitive. So T1 is similar to T3, and these selection of words lead me to that enforces me to write T1, T3 pair belongs to R. So T1, T3 belongs to R. So R is transitive. So given R is reflexive, symmetric, transitive, meaning is an equivalence relation. Clear? This question. Show that the relation are defined in the set A of all polygons. So set A is of all polygons. Now this R is defined as collection of all pairs P1, P2 such that P1 and P2 have same number of sides. Simple. And we have to show that this R forms an equivalence relation. You'll have some seconds to try this problem, then afterwards we will move on to the solution slide. So your time starts now. The time is up. So in question, we have to show the given R is an equivalence relation. Solution. So in order to show equivalence relation, we need to fulfill three types of relations. So reflexive, symmetric, transitive. So for first, consider a polygon P1 which belongs to the set A, obviously. Now this P1 has same number of sides itself. Yes. So we can easily write P1, P1 belongs to R. Why? Because we know any pair belongs to R when both polygons have same number of sides, and we know these are the same polygons, so same number of sides. Now R is reflexive. For symmetric, we start with a pair belongs to R. So P1, P2 belongs to R. If this pair belongs to R, meaning both polygons have to satisfy the condition. So P1, P2 have same number of sides. Using different words but the same meaning. So P2 and P1 have the same number of sides. Yes. And these selection of words enforces me that I can write P2 comma P1 belongs to R. Why? Because P1 and P2 both have same number of sides. Now R is symmetric. For transitivity, we start with two pairs, P1, P2 belongs to R, P2, P3 belongs to R. And we know from first pair, P1, P2 have same number of sides, and from second pair, P2 and P3 have same number of sides. And we know P1, P2 have same number of sides. Suppose n, then we know P2 have say n number of sides. This gives me P2 and P3 also having n number of sides. So from here, I can easily conclude that P1 and P3 have same number of sides. So P1 and P3 have same number of sides. Therefore, P1, P3 pair belongs to R. R is transitive. What we have shown is simply R is reflexive, symmetric, transitive, which imply R is an equivalence relation. I hope this is clear to you. Moving on to next. This question. R, this relation R in set N, set of naturals, is given by collection of all pairs A comma B satisfying the condition A is equals to B minus 2 and B is greater than 6. Then we have to choose the correct. So we have to choose the correct. So simply for A says 2 comma 4 pair belongs to R. We have to see is it belongings to R. For B 3 comma 8 belongs to R. For C 6 comma 8 belongs to R. For D 8 comma 7 belongs to R. So we just have to choose the correct option. Simple. You'll have some seconds to try this problem, then afterwards we will move on to the solution slide. So your time starts now. The time is up. So in question, R is given to us in set builder form and we have to choose the correct option. Solution. So analyze the options. Simply 2 comma 4. So A is 2, B is 4. Now check for the condition A is equals to B minus 2, which is true. So this condition is true. Now for second condition, B must be greater than 6. Here 4 is not greater than 6. So false. So both conditions are not satisfied. So this pair not belongs to the relation R. So 2 comma 4 doesn't belongs to R. For second, option B 3 comma 8 pair. A is 3, B 8. A is B minus 2. If you try to see what's happening, is simply A is equals to B minus 2. If A is 3, B is 8, just put A 3, then 8 minus 2 will be what? Your 6, which is not true. Now for second condition, indeed second condition is satisfied. Why? Because 8 is greater than 6 while first is not. So 3 comma 8 does not belongs to the relation R. Now for third part, 6 comma 8. A is 6, B 8. Check for this condition, A is B minus 2. So 6 is equals to 8 minus 2, indeed true. For second condition, B is greater than 6, indeed 8 is greater than 6, true. So 6 comma 8 pair belongs to R. Clear? Now for fourth, from option D, 8 7. A is 8, B 7. A is equals to B minus 2. So 8 is equals to 7 minus 2, false. Therefore 8 comma 7 doesn't belongs to R. Simple. That's the correct option, simply C. I hope it is clear to you. Moving on to next. Now this question, show that the relation R in the set A is given in this roster form 1, 2, 3, 4, 5. Given relation R, collection of all pair A comma B such that absolute of the difference A B is even. And we have to show the given relation R is an equivalence relation. You'll have some seconds to try this problem, then afterwards we will move on to the solution slide. So your time starts now. The time is up. So in question, we have to show that the given relation R is an equivalence relation. Solution. Starting with set A given in roster form, relation R, set builder form, collection of all pair A comma B such that absolute of A minus B is even. It is clear that from any element A belongs to A, we have absolute of A minus A 0, which is even integer. Therefore R is reflexive. Now A comma B belongs to R, meaning the absolute of A minus B is even. This gives me absolute of minus of A minus B, which can be rewritten as absolute of B minus A, which is also going to be even. So B comma A pair also belongs to R, meaning symmetric. So R is symmetric. Now for transitivity, starting with two pairs, A comma B belongs to R, B comma C belongs to R. From first pair, absolute of A minus B is even. From second pair, absolute of B minus C even. So A minus B even, B minus C even. So assuming that A is greater than B greater than C, so we are having A minus C is equals to A minus B plus B minus C, which is even. Why? Because sum of two even integer is even. We can easily conclude that absolute of A minus C is also even. So A comma C pair belongs to R. Therefore R is transitive. Hence R is an equivalence relation. I hope it is clear. Now this question, show that the relation R in the set A of all books in the library of a college given by collection R given by collection of all pairs X comma Y such that X and Y have same number of pages. And we have to show that this R is an equivalence relation. You'll have some seconds to try this problem, then afterwards we will move on to the solution slide. So your time starts now. The time is up. So in question, we have to show the given R is an equivalence relation. Solution. Starting with set A, which is your collection of all books in a library of a college. And R is collection of all XY such that XY both have the same number of pages. R is reflexive. Why? Because X comma X pair belongs to R. Why? Because X has the same number of pages as itself. Now for symmetricity, we start with X comma Y pair belongs to R, meaning if this pair belongs to R, meaning both books have same number of pages. And the same thing can be said by these words. So Y and X have the same number of pages, which lead us to Y comma X pair belongs to R. Therefore R is symmetric. Now for transitivity, starting with two pairs X comma Y belongs to R and Y comma Z belongs to R. From first pair X, Y, both books have same number of pages, and from second Y, Z have both same number of pages, and this gives me X, Z have same number of pages. Why? Because Y is having same number of pages with X, and Y is also having same number of pages with Z. So this can only happen when X and Z have same number of pages. So this pair XZ also belongs to R. Therefore, R is transitive. So what we have seen is R is reflexive, symmetric, transitive. This implies R is an equivalence relation. Clear? This question, show that the relation R in the set 1, 2, 3 given by collection of these two pairs 1, 2 and 2, 1 is symmetric but neither reflexive nor transitive. You'll have some seconds to try this problem, then afterwards we will move on to the solution slide. So your time starts now. The time is up. So in question, we have to show the given R is symmetric but neither reflexive nor transitive. Solution. Relation R is symmetric when if you pick any pair A comma B from R, then B comma A also belongs to R. So we are only having two pairs, so pick any. For now, if you choose this 1, 2, we can easily observe that 2, 1 also belongs to R. If you pick this 2, 1, then we can easily observe that 1, 2 also belongs to R. So for every pair, if you choose any pair from a relation R, we are having the condition B comma A also belongs to R. So symmetric. So we have 2, 1 belongs to R, the reverse pair 1, 2 also belongs to R. So since both conditions are satisfied, we conclude that R is symmetric. Now for reflexive, we know that A comma A belongs to R for every A in the domain set, and set is this 1, 2, 3. This gives me that 1, 1 must belongs to R, 2, 2 belongs to R, 3, 3 belongs to R. But here none of the pairs belongs to R, so not reflexive. So the elements in R set are 1, 2, 3. So 1, 1 not in R, 2, 2 also not in R, 3, 3 also not in R. So not reflexive. The same goes for transitive. If you choose any two pairs, so we are choosing 1, 2, 2, 1, and then if it is transitive, then 1, 1 must be in this relation R. But you can easily observe we do not have the pair 1, 1, so not transitive also. So for transitive, so far we have seen these pairs not belonging to the relation R, so not reflexive. And as I have already told you that for transitivity we require two pairs A comma B, B comma C belongs to R, and we need to show A comma C must also belongs to R. But whereas this case is not satisfied here, and we can see by these two pairs 1, 2, 2, 1 belongs to R, while 1, 1 doesn't belongs to R. So 1, 1 is not in R. Since we found a case where the transitive property doesn't hold, so we conclude R is not transitive. So what we have shown is the given R is symmetric but neither reflexive nor transitive. I hope it is clear. This question, show that the relation R in R defined as, so R is your, this R is your set of reals. So R defined as relation R is collection of A comma B such that A is less than equals to B. And this relation is reflexive, transitive, but not symmetric. You'll have some seconds to try this problem, then afterwards we will move on to the solution slide. So your time starts now. The time is up. So just show the given R is reflexive, transitive, but not symmetric. Solution. Given R collection of all pairs A comma B such that A is less than equals to B. A, B all belongs to the set of reals. So if the relation is reflexive, then A comma A belongs to R. And we know indeed A is less than equals to A, which is true. So it is reflexive. If the relation is symmetric, then if you start with any pair belongs to R, then we need to show that B comma A also belongs to R. So if this pair belongs to R, meaning A is less than equals to B, then B is less than equals to A. Is it always true? So if you pick A2 and easily observe that A is less than equals to 5, but 5 is not less than equals to A, so not symmetric. Clear? So if you take, we have taken B5. If you take B5 or 22, the same goes. So condition is not satisfying, so relation not symmetric. Now for transitivity, starting with two pairs belongs to R. So from first pair we have the condition A less than equals to B, and from second we have the condition B less than equals to C. So we can easily conclude that A is less than equals to C. So A comma C pair belongs to R. Therefore R is transitive. So what we have shown is the given relation is reflexive, transitive, but not symmetric. We have seen counter examples. Clear? This question, show that the relation R in the set of reals defined as collection of all pairs A comma B such that A is less than equals to B square is neither reflexive, nor symmetric, nor transitive. You'll have some seconds to try this problem, then afterwards we will move on to the solution slide. So your time starts now. The time is up. So we just need to show that the given R is neither reflexive, nor symmetric, nor transitive. Solution. Check for reflexivity. A relation R is reflexive if for any element from the set of reals, the pair A comma A also belongs to the relation R. This means that we need to check the condition A less than equals to A square for all A belongs to the real numbers. So if you try to see, if you take A 0.5, then its square will be 0.25, and this condition not satisfied. So false, meaning not reflexive. Now if you pick A is equals to -1, then -1 less than equals to -1 square. Indeed it is true. So we have seen an example which do not satisfy the condition. So not reflexive. Now for symmetricity, if A comma B belongs to R, then B comma A must be in R. Now we just have to find an example where A comma B belongs to R, but B comma A doesn't belongs to R. So if you pick A1, B2, then 1 is less than equals to 2 square. Indeed true. While, so what we have seen so far is 1 comma 2 pair belongs to R, while 2 comma 1 pair doesn't belongs to R, because 2 is less than equals to 1 is not true. So this is false, meaning 2 comma 1 doesn't belongs to R. Since we have found an example where A comma B belongs to R while B comma A doesn't belongs to R, so not symmetric. Now for transitivity, check for transitivity. So for transitivity, what we start with simply with two pairs A comma B comma C both belongs to R, and we have to observe that the A comma C pair belongs to R or not. If it belongs to R, then it is transitive. If it not, then not transitive. So picking ABC as 2 minus 2 minus 1. So for AB, 2 is less than equals to minus 2 square, which is true. Meaning 2 comma minus 2 pair belongs to R. For BC, minus 2 is less than equals to minus 1 square, indeed true. So minus 2 comma minus 1 belongs to R. Now for AC, A is 2, C is minus 1. So 2 is less than equals to minus 1 square, which is not true. So 2 comma minus 1 doesn't belongs to R. Since we have found an example where A comma B belongs to R, B comma C also belongs to R, but A comma C doesn't belongs to R. So not transitive. So the relation is neither reflexive, nor symmetric, nor transitive. I hope the counter examples are clear to you. So this is it from this session. Thank you.